Um, oh, there are. Okay. So if I speak up that way, then. Oh, okay. Well, thank you, and thank you for the introduction. I hope that by anchor you don't mean pulling us down underneath the water. Yeah. Okay. Okay. Well, thank you very much for the invitation. I'm very happy to be here and to present this work to you here today. I have really two goals that I'd like to accomplish, and one is to tell you about what Troy mentioned, this Transport Model Validation Task Force at DIII-D. And that would be the first goal, to tell you a little bit of what we're doing there. And then the second goal is to give you an idea of what we think we know about very high K ETG scale fluctuations. And they're going to be higher K than what Lothar has just shown you. And on this slide here, I've got, just to start out with the TMV. The TMV was instituted at DIII-D about 2 years ago. And it's what's called a task force, but it's really, you can think of it as a working group, or a group that's loosely aligned. It consists of many different participants, and this is in alphabetical order here. General Atomics, MIT, PPL, UCLA, UCSD, University of Colorado, University of Wisconsin. And here's a list of the names, and I suspect I haven't gotten everybody. So if somebody doesn't see their name or knows somebody that's not on there, that should be on there, let me know. But to give you an idea, it's not an exclusive group. This is a group of people that are interested in working on comparing measurements to simulations, and those simulations are not limited to any one particular model. It's completely open. Anybody that's interested in joining and participating in this group is welcome and encouraged. In fact, as you'll see, and maybe as you sort of saw today, and as you'll see here, we need a lot of help. There's a lot of work to be done. We actually have a tremendous amount of data. And that data needs to be compared to simulations, and it's a lot of work, as many of you know. It's a lot of work to do that. And this, I'm not going to go over this right now, but I'll come back to it a little bit later. Okay. Well, what are we dealing with? Verification deals with mathematics, whereas validation deals with physics. This is a quote. Validation addresses the physics modeling accuracy of a computational simulation by comparing the computational results with experimental data. And here I just want to point out that I really prefer the nomenclature validation studies, as this avoids some perceptions in the English language when I'm validating a model, there's some perception that it's right. That it's right. I'm just showing you it's right. That's right. That's okay. Okay. Well, maybe I'm preaching to the choir here, as they say. Anyway, I prefer that kind of nomenclature, and that's the way I'll refer to it. So the outline here is I'm going to briefly go into a little more detail on the TMV work that we're performing there. I was going to give you a little bit of an update on this elongation experiment work that's going on. I think what I'm going to do is defer that and go directly to the high K density fluctuation data and hold that for, if we have more time or. Okay. So within the TMV, our approach is we'd like to compare measurements to the simulation, but we'd like to do this in some sort of manner that makes sense. And what we do is we look at parameters that have a very strong response in the plasma. And this is a table, this is just a representative table, showing some response of the chi's to these different parameters. And for example, rho star is you probably are aware, is something that affects the transport. George, I think, talked about that earlier today. Q, the safety factor, affects it. Kappa, the elongation of the plasma, certainly has a very strong effect. TE over TI also has a strong effect. So what we do is we will choose one of these parameters and design an experiment that will take advantage of that parameter and trying to hold these other parameters in some sense constant. And really what happens is that's a very difficult, it sounds simple, it turns out it's quite difficult to design these experiments because not only do we have to try to hold these other parameters constant, we have to make a plasma that allows access of all our diagnostics. And then Ann showed you this earlier, and I think this is a good representation of what's going on. You see up above a sort of representative turbulence mechanisms versus K, and in the low K, intermediate, and very high K. And then this is the sort of the diagnostics that we have on DIII-D currently. And those cover, in terms of density, a very large range of K and a large range of the radius. And many of these, most of these, have good spatial resolution, although not all of them do. Okay? Most of them do. And then, as Ann pointed out, there's these other fields that have recently been added. Electron temperature fluctuation, flows, GAMs and zonal flows, as George and Lothar pointed out, and then the NT crossphase as well. So what we try to do is take advantage of all these diagnostics that we have on DIII-D. We try to take advantage of DIII-D itself. It has a lot of different heating capabilities. It has neutral beams, fast waves, and ECH. The shaping capabilities are pretty nice. We're able to have a lot of different shapes in a very controlled manner. Let's see. Yeah, okay. So, like I said, what we try to do is design these experiments so that we can use the diagnostics we have. And then we go and as you know, we only have certain parameters that we can control. We put in a particular magnetic field, power of injection, shape, and we sort of, in some sense, give that to the tokamak. And then the tokamak does what it wants. It gives us back something. And often, if we've done our job right, we get the shape and the parameters of interest. And then this is where it becomes sort of tricky, because now we make measurements. And we make those measurements with all of the known uncertainties and systematic offsets and errors and things. And then those things, those profiles are then put into the codes and simulations. The simulations then will make a prediction, say N tilde or T tilde like you saw earlier, and then we make these other measurements of the same parameter. We compare them using these simulation or the simulated diagnostics so that we feel like we're comparing apples and apples. But you can see here, it's this, to my mind, this is a sort of an interesting thing, because this is where all the uncertainties and errors actually enter into the codes and simulations themselves. Okay? And so we end up with something, and then we ask the question, are these results within the requirements? And then this is another, to my mind, this is a sort of a gray area. I think this is an area that we haven't really thought about a whole lot, because as scientists, we think when we compare something, we compare it, if we get agreement within the error bars, it's good. If it's outside of the error bars, it's not so good. And that, I think we all feel pretty good about that. But in the end, what is it we really want? I think Steve Calley this morning talked about predicting performance of either, of every shot. And that might not be quite the same thing as having identical, predicting every quantity within the uncertainties. You might be able to predict the performance of the shot without predicting every quantity exactly. And this is just something that, it's one of my thoughts that I've been thinking about, that we need to really, I think, look at this. In terms of the, I think it's something that we need to really sort of consider. So what we do is we design our experiment. Typically we use simulations ahead of time to look at the experiment to make sure that the simulation is going to predict a large response. Okay? And so then we go in and we make multiple measurements using repeat shots, and we take many measurements in order to beat down these uncertainties so that we, in this little leg of the diagram, so that that is as good as we can get it. So the approach is both qualitative and quantitative, and that is that what we'd like to see is a qualitative agreement between what we measure and what the simulations predict. And here I've got an example of a kappa change where we have a high kappa plasma and a low kappa plasma. And this is an experiment that we performed on DIII-D. And the prediction was that the low kappa would have much larger transport, larger fluctuation levels than the high kappa. Now, that's a qualitative prediction, and what we saw qualitatively in the experiment on the day was that that's what we had happen. We also looked at these other parameters. This year we spent a lot of time on TE over TI, some time on rotation shear. Last year was grad TE behavior, or 1 over LTE behavior, or kappa scans. We had a lot of data on the phase angle between NT and talked about that. We have some other interesting possibilities as we go forward. So we have the qualitative agreement that we like to see, but then we need to have a quantitative agreement, and that is that we'd like to see that this is a measure of T tilde over T versus rho for the low kappa. You can see it's got a larger, rho is the minor radius here. You can see it's got a larger fluctuation level than the high kappa case, and qualitatively that's in agreement. So we'd like to see from the simulations not only this qualitative change, but the quantitative behavior. In other words, we need to see it predict the absolute level of T tilde over T and this change in T tilde over T, and also this radial behavior. And we'd like to see that in multiple fields, density and temperature, for example. Mentioned multiple radii, the multiple scales. This is low K T tilde. We'd like to see this over the range of scales that we're capable of measuring from ITG up to ETG. And then we'd like to get it into very detailed quantities such as the NT crossface, K-spectra, and correlation links that George and Ann and Lothar talked about.
Are these two plasmas done with the same plasma current?
Well, yes, in this case. Well, in this case, yes.
At the same Q, the left plasma could have held a lot higher current. And that's where a lot of the favorable kappa is coming from.
Yeah.
But this was done at fixed current, you're saying?
Yeah.
Okay.
I mean, what you're doing is, you're pointing out, it's one of the things that we run into is we cannot hold everything
But
constant.
you can vary the experiment and the simulation in the same way. So I just want to.
That's right.
What it is.
That's right. That's what we'd like to see is yeah, that's right. Let's see. Okay. So these are the experiments that we ran this past year. Was this TE over TI scan? We did this in QH mode. Lothar showed some of that. We also did an L mode and a hybrid H mode scan for that. And we had 3 days of experiments, and we used those for those days. And let's see. So I pretty much went over that, I think. Okay. All right. So that's the overview I had really for the TMV. Does anybody have any questions about that before I move on to the high K? Okay. All right. Okay. All right. So this is switching topics, and what I'm going to do is look now and try to give you some idea of what we think we know about high K ETG scale fluctuations on DIII-D. And here what I'm going to do is give you a little motivation why it's important to look at that, describe the diagnostic itself, the experiment and the results, and make some comparisons to linear and nonlinear gyrokinetic simulations. Now, I think, as you know, the source of electron thermal transport is not well understood. There's many instabilities that are sort of available to explain it. In particular, the ETG scale, which is K rho I or K rho S greater than 2. These high-frequency high-K modes are predicted to drive varying levels of thermal heat or thermal transport. And this is represented by some of the papers here. And these predictions range from small to quite large, depending upon the model in the plasma. And this is motivated experiments on various machines. Now, the results I'm going to show here today are what I think is the most complete results we have from DIII-D, and it's work that we could essentially from about 2006. So this is about 4 years old now. We haven't really returned to this in great detail since then, although we continue to use the diagnostic. These experiments I'm going to describe to you today are the most complete in terms of the high K. What the diagnostic itself uses collective Thomson scattering. It uses momentum matching for the K. You have for forward scattering, you have an injected wave that then interacts with the density fluctuation of the plasma. It scatters the scattered K at some angle theta, and then if you look over here, you can see that scattered signal. For 180-degree backscattering, the wave injected goes in here. It interacts with a very high K, which sends it back on itself here. And this conserves momentum and energy. And you can see that the K, in this case, is quite, or the wavelength here is quite long compared to the wavelength here. So this is a very high K that sends it back on itself. And this is the process that we use for the high K backscattering system. And this is a diagram of colloidal cross-section where we inject 94 gigahertz radiation in here. There's a 94 gigahertz electron cyclotron resonance at this location in this plasma, which acts as a beam dump. It absorbs the radiation. And what we get back is this backscattered radiation at the reverse K, which is about 35 inverse centimeters. And for this diagnostic, it's a radial K. You can see it's almost purely radial. It has very good delta K. For this view here, there is no spatial resolution at all. It's a chord from the edge into this resonance region because it can scatter at any location along there. We have a second view, which is purely passive, which is the cross-section, or the intersection of this view with this probe beam. And in this case, the localization is much better because it's defined by the intersection of these two beams. And this is the one I'll be telling you mostly about here today because this does give us some spatial resolution. And we're able to move the position of the scattering in this plasma by, if you move this receiver either up or down, you can see that this intersection moves either in or out because of this angle that the probe beam goes in at. So this is not reflectometry, it's scattering. Typical K rho I values are 4 to 10. The typical resolution for this view here is plus or minus 10 centimeters. And remember, DIII-D is about 63 to 67 centimeters in minor radius in this plane here. Okay. Okay. All right, now let me just use this one more time here, and that is what we do in the following experiments. We add ECH heating. ECH heating on DIII-D is localized, and we add it in about this location here, and I'll show you on a radial profile later, but just to give you a geometric view of it, it'll be right in about that location, about row of 0.6. And these are radial profiles of the different parameters. Over here is TE. The black is the ohmic case. Red is where the ECH is added. The ECH is added here, and this is the heating profile here, so you can see it's fairly well localized. TI does not change much with the ECH. NE remains roughly the same. There's some small changes in scale lengths, as you'll see. Q profile doesn't change. These are the scale lengths here, and you can see that in the radial region in the core between of interest, about 0.3 to 0.8 or so, there is a small decrease in this parameter A over LTE. There's certainly a change in the TI scale lengths. NE scale lengths, you can also see there's some small changes. And the magnetic shear is unchanged in this case.
How is it that A over LTI changes so much with the high temperature?
I think this is a this is in some sense an artifact of these spline fits to the data that we use. You know, you can see, you probably can't see because the projection's a little weak here, but if you looked in detail, or if I could expand this, you'd see that those profiles, although they overlap in their uncertainties, you know, those dotted lines are the uncertainties, or these gradients are quite different in there.
So in other words, what you're showing are fits, right? Not the...
I'm not showing you the real data. That's right. I could. I don't have it with me right now, but I could show it to you. And there would be lots of dots on there.
But nevertheless, the right curves are the gradient of the left curve.
That's right.
And so this is just showing that you can have significant durations in grad T, and as long as it's over a narrow region in R, it doesn't change the profile much.
That's right. That's another way of looking at it. And the other way to look at it is that these are the profiles that will then later go into the linear and nonlinear simulations, because we have to have some smooth profile or fit to go into these simulations. We don't really use the real data. So yeah. So I think this is one of the issues right here. So what did the transport do? This is the thermal flux here, and this is the total thermal flux. The electrons and the ions added together. Black is the ohmic, and you can see that when we add the ECH here, there's a large increase in the thermal flux right at that region here. And this is primarily due to the electrons. Similarly, with the chi's, this is again the total chi. You can see that the chi interior actually goes down a little bit and increases quite strongly here. This is a log scale versus minor radius. And for reference, the neoclassical chi's are shown down here. Okay, so we had a large change with this heat that we added. And what was the response of the fluctuations? What I'm showing you is the high K backscattering. This is about 35 inverse centimeters here in terms of K. This is K radial, remember, from 3 radial positions, and those are indicated here, here, and here. And so these are 3 different shots. They are mostly the same. The ECH comes on at about 2200 milliseconds and then goes off at about 3500. You can see there's some the red, I don't know if you can see this in the back, but there's some red, which is neutral beams that we put in for diagnostics. Slightly different. There's a neutral beam that's slightly earlier here, it's later here. And then I won't talk about this part here, but this is quite interesting if we had time. So what did we see? Well, at the edge, you can see that it gets very bright. And then let me just explain. This is a frequency versus time, and power is shown here. Red or yellow and white is large power, blue is small, and so you can see it's going from high power to low in terms of the fluctuations. And so you can see it gets very bright when the ECH comes on. It gets very bright here. And in contrast to that, in the very core, it gets less bright. And so from this, you might think that, well, this is going down here and going up here.
Sorry, I'm confused. I
Yep.
thought you said that this high K channel could not be scanned and was averaging over 30%, 70% of the
Yeah, I was trying to be clear about that, so let me go back. What I was trying to say is this
That's the 30, that's the K.
That's the K radial that cannot be scanned. That's just going to give us a chord average measurement. This channel, which is purely passive, gives us spatially localized information because it's defined, that spatial localization is defined by the intersection of the two beams, if you will. If you can think of this, it doesn't inject any power, but it has some antenna pattern which defines a beam.
Right, but you said the second one is that K equal to 20 inverse centimeters.
K equal 20. Yeah, this is, okay, this is this is sort of an artifact from this.
Okay.
We had at that time, we had a high or an intermediate. Okay, now.
I guess I understand now.
Okay, you should just ignore that.
Okay.
Because because these work off the same frequency, it's the same, nearly the same K. The K being different by this really small angle.
Okay.
Okay, so that's probably my fault for leaving that there. That's another channel that I'm not talking about. So we do this data is spatially localized, and we can move it around by moving the vertical position of this channel here, by moving it up and down, and it scans that in and out. Okay, and that's what I did, or that's what we did for this data here. I hope that's clear. Okay, so, all right. I mean, this gives you a qualitative picture that something sort of dramatic is happening here, here, and here. And you'd like to quantify that, and it's shown here. So what I'm doing is apply to the ECH power versus time. And this is the RMS fluctuation levels for those three positions, edge, mid-radius, and core. And you can see that the sort of the ohmic fluctuation level at the edge is here. The ECH comes on, it increases maybe 20%, 25%. The mid-radius, you see a larger increase. And in the core, you can see a slight decrease of maybe 10% or so. And this is consistent with your qualitative picture of those spectrograms that I showed you earlier. These high-frequency hash here, this is sawtooth, this is a sawtoothy plasma. So what I can do is then I can look at and compare the fluctuation level here in ohmic to the fluctuation here with the ECH and ask what that change is, and that's shown here. So this is just quantifying those changes at the edge, where we see about a 40% change going up to about 55% positive. Remember, ECH heating is here. And then decreasing about 15% in the very core with the ECH. And now this is a normalized fluctuation level. It's normalized to the ohmic fluctuation level. And you can go back and compare that to the thermal fluxes that I showed you earlier with the ECH, where we see a very large change out here in the thermal flux and a decrease in the core. So there's some qualitative, but not very quantitative agreement there. This is sort of interesting. What we said, well, it's okay. We heated with the ECH at rho of 0.6, and we saw the core decrease. What if we put the heat at rho of 0.2? And we did that, and here's the ohmic temperature profile. The ECH temperature profile is shown here with the heating at rho of 0.6. And here you see the TE profile with heating at rho of 0.25. It's a very different profile. Okay. The scale lengths changed in this region where we're measuring. It's shown here. The scale lengths in ohmic about normalized 2.5. With heating at 0.25, it went up to 3.5. And at 0.6, it went down to 2. And this is the corresponding spectrograms here and the corresponding RMS fluctuation levels, the changes. And so what you see is when we heat in the core, where the scale lengths increase, we saw an increase in the fluctuation levels here. This is heating in the core. And when we heat out at rho 0.6, the scale length decreased, and we saw a decrease in the fluctuation levels. So it sort of confirmed that we were at least, it was an instrumental effect, if you will. Now, we compared it to a linear gyrokinetic code, GKS, at that time. And this is, I'm afraid black and red is not really the best here, but ohmic is black. And now what I'm showing is a growth rate, a linear growth rate, gamma, versus k theta rho s. And this is the ohmic black here. And this is rho 0.35. And the red, which cuts off here, is the ECH case. And this is the measurement region arranged for this high K measurement here in terms of K rho S. And what you see is that when the ECH is added in the core, the linear code predicts no instability in a linear sense for Ks above about K rho S of 1. Out at R over A of 0.6, the behavior is different. We do see a decrease in the growth rate, but it's not a tremendous change in terms of what we saw back here. And we in fact saw a small increase here with the ECH. So this was, in some sense, qualitatively consistent in the core. And here we don't think that that was really qualitatively consistent, since we saw an increase in that region, and the linear prediction would be a slight decrease. Again, it's linear, so it's not fully.
On the other hand, if you have an increase at low K, right? So
yeah, we do.
some kind of a cascade or whatsoever, you would.
Yeah.
Maybe what you're doing is just pumping fluctuations at high K, which are not representative of what is locally going on for the linear growth rate.
Yeah, exactly. That could exactly be the point. And so we would need some non-linear simulations to sort of sort that out. Yeah, yeah, I think that's right. So. And, okay, so just focusing for now on the very core, sort of asked, well, we saw this change in, here the ohmic growth rate is shown here in is sort of light gray, and the ECH growth rates in the red here versus k theta rho s. And we asked the question, well, what happens if we used A over LT near the ohmic value and use TE at the ECH value? In other words, you're trying to separate out, in some sense, what is making this K range go stable. Is it the change in TE? Is it the change in LTE? What is it? And what we saw in that case is the growth rate actually went up. So it wasn't TE change that did it. And then what we did is, the green is we took the TE near the ohmic level, and then we took A over LTE, the scale length at the ECH level, and we saw it go down. Okay. So at least it went in the right way. It didn't fully suppress. There's a region here where it did change. So at least it's sort of, went it the right way. And one conclusion from that is that, well, at the very least, A over LTE, the change in A over LTE is one of the dominant terms here. And that's what we saw with the case when we put the heating in the very core. We compared the data to a critical ETG scale length prediction by Yinko et al. And this is, what I'm plotting here is this calculation of the critical scale length prediction versus R over A for the ohmic case, which is black, and then the ECH case, which is the dotted red, and 0 is here. And so you can see that in the towards the edge, the critical gradient goes up with the ECH, and the core, it's predicted not only to go down, but it's go down below 0 here. And so in some sense, it would be stable here, which is consistent with that, the GKS calculation. And here you see that there is some qualitative agreement here. We see an increase here. Here, again, we see an increase, although both GKS and this seem to say that it should go the other way. And we see some qualitative agreement here. Although, again, we saw finite levels of fluctuations there. They weren't fully suppressed. Okay. So, next, what we did is we looked at gyro, and this was, I think, gyro, as you probably know, it's a physically comprehensive nonlinear gyrokinetic code. It contains many of the things we think are important. And this was, again, 4 years ago. What we did is they did use a real mass ratio, 60 on this, and the runs were about 36 hours on the 640 processor Cray XT4. We did use the experimentally determined profiles that we were discussing earlier as the inputs. Only one position was looked at. So this was a very big run for us at that time, and it took quite a bit of computational resources. And this is the results of that. And we see this is a K theta rho I and K radial rho I here on this axis. In the ohmic and ECH case, this is n tilde over n squared. The measurement region of the diagnostic is shown right. I know you cannot see that, but there's a little square there. This one's a little more visible, but not much. In any case, it's a, let's see if I can get this. It's a very small square in terms, it has a very small K theta response and not a very big KR response, and it's up at fairly high KR. It's a little over 7 in this case here. Okay. This simulation was run, and it did not really reproduce the chi-E's very well. It's about half of the chi-E experimental. It turned out it was very sensitive to the ion drive. A small change in A over LT of 20% would result in about 200% change in the chi total. So there's a lot of sensitivity there. We did not at that time have a synthetic diagnostic for the high K diagnostic itself, and I don't really know if that would have helped, because this, this was a flux tube simulation. So with the high K, it's going to cover many flux tubes. So it's not quite clear that would even have helped. But in any case, we did not get very good agreement between what we measured experimentally in terms of the thermal transport, and we didn't get any good agreement with the high K measurements. And again, it's with the caveat that we didn't have a synthetic diagnostic here. And that is that these, I know you can't tell it here, but there was virtually no change in these fluctuation levels here and here. What you can see is that as we go from the ohmic to the ECH case, the K theta here is suppressed quite a bit. There's a very large change here. Okay.
But this is all numerics. So where's the agreement?
What's that?
This is all numerics.
This is numeric. This is numerics, absolutely.
Can you overlay your spectrum on numerics?
Well,
They just have a point.
okay, that's what I was trying to make.
That's it.
I mean, what we have is data from that point right there. Okay, so I could overlay it. I could show you later. I don't have it on this.
What color is it?
That's I sympathize 100%, 1,000% that you cannot tell what that is. Let me get the rod.
No, but this red square is red because that's where it's not actually red on the same scale as
It's just to show.
It is not. It is. If you took away that.
So what color is it on the
Okay.
color
Okay.
scale?
Okay. If you took away that little square, that rectangle, it would be roughly the same color as the surrounding.
Right.
Like,
That's
there's
the
no.
code. How about the measurement?
Well, okay. You're saying. I'm not quite sure what you're asking.
Well, I'm saying, you've.
We saw an increase. You saw that increase, right? Let me go back. Let me go back. I know this is like throwing a lot of stuff at you guys.
Is there a quantitative agreement between what the code says delta n over n is going to be and what the experiment says?
We don't have quantitative. We have disagreement.
Okay. So
Say we have disagreement. We see it. This is where we're doing the simulation here. We see a huge increase, more than 50%. Okay? The code predicts no change in that case.
But did the code predict a change in chi-E?
It did, but it was the wrong. One thing is the wrong direction, but it was also the
So
It missed.
as you point out here in this bullet, 20% changes in the gradient will give rise to 200% changes in current.
Yep.
So it'd be best to try to do a flux match
Yep.
comparison.
Yeah, that's
If you
right.
ran gyro in a way that it matched the heat flux, does it predict the change in the signal?
Well, this was done in 2005, 2006, and that was just when all that was coming on board. So we had not revisited that. So I think you have a good point. Is we should do that. We knew at that time that there was something there that we could do, but this is sort of a heroic run. This is a coupled ITG, TEM, ETG simulation. So we weren't able just to make another run, change it and make another run. So yeah.
In that case, couldn't you just change the experiment to fit the simulation?
What's that?
Couldn't you just done lots more experiments to fit the simulation instead then?
I mean, one of the experiments might fit that particular simulation.
Yeah.
If your scatter was high enough, you mean?
In other words, if it's too hard to do the code, do the experiment, right?
Yeah. But is that going to validate the code?
Yeah, but it's the onus is on the code to work, not on the experiment, right? I mean,
We know the experiment works, don't we?
well, exactly, right?
Yeah.
It's the code's problem, actually.
Yeah. Hey, this is your problem, not mine. I mean, I think what you're. I'm sort of. I understand exactly what you're saying, and this is what we've been saying. This is one of the great difficulties we have with this is that you can go down there and in a day take a tremendous amount of data, and then it'll take a year of concentrated effort to make these comparisons. So we really need. It takes a lot of effort. I think I know
Is that
some.
what you're saying, Terry?
What's that?
We need more money.
Did I say that? Yeah. Yeah.
What are we in this context?
Yeah.
Yeah, right.
Go for more money.
I said you need more.
Oh, did you say you?
We need more money too.
We need more people too. So but money, people is sort of the same. Okay, so the summary for this section is here that we observe this high K turbulence, and it's in an ETG wave number range, and I think we have really strong evidence that it correlates with the electron temperature scale length. We saw this very strong radial dependence with the ECH heating, and we saw a qualitative similarity between the changes in the high K, N tilde, and ETG critical scaling formula, as well as the GKS linear growth rate calculations. These coupled ITG, TEM nonlinear gyro simulations performed. They used a real mass ratio. They were unable currently to match the experimental transport levels or the fluctuation level changes. Let me put it that way. The fluctuation changes that we saw. So we weren't able to get the qualitative agreement, much less quantitative agreement at this point. And as I mentioned earlier, one of the things we wanted to start with was a qualitative agreement, and then you move on into some quantitative studies, and we weren't even there with that. So we have a lot of work to do with that.
Does this mean there is no reliable numerical prediction? Or is that a bit too strong a statement?
That might, I don't know that I would say that.
You should
Could you
address
show
that
the
with
pod
fields.
versus radius? You showed the three different radii that how the density varies. Well, first, is this your last slide?
This is, I think, yeah. Yeah.